specificity. So the way it will work then is through either DNA repair, through homologous recombination repair, where if you include a donor, or you can integrate in a sequence, or it will introduce non-random point mutations, target deletions, or, as I say, if you put in a donor, you can get a DNA fragment. Equally, you can have error-prone non-homologous end joining, and this will induce deletions, insertions, or substitutions, and that's where you're going to get your loss of function phenotype, because it's going to have a frameshift mutation or it'll truncate your protein. Now, the way it has been adapted by several groups to try and not induce repression rather than a complete DNA editing is to use a Croppel-associated box of Crab domain, which is then fused to this one of the DNA binding domains in this case, that will target a transcriptional start site. So effectively, it will just sort of sit there and it will block the ability of the transcription to occur at that site. Now, the disadvantage is you have to often test different sites within the transcriptional start site to avoid the occupancy of where the core promoter is. So you've got to be able to actually interact at the site to block where the transcription factors are going to be fine, or where there's high nuclear zones. So actually being able to design these can be quite difficult. As a monomer, these can induce off-target effects. That was the advantage of here, where you have the double. This is less non-specific than here, where you tend to have a risk of off-target effects, because trying to find these sequences can be quite difficult. But a lot of groups have used them. They've been less used in the context of screening. So now I want to turn to what I'm sure everybody in this room has now heard of, and actually just out of curiosity, so how many people have actually done CRISPR experiments? Okay. I'm trying to get a sense, across the campus, we're trying to get a sense actually of how many people have done siRNA experiments or RNAi experiments? Okay, all right. And how many people have done TALEN experiments? And I know I can't see what everyone looking on the web is doing, but we're just trying to get a sense across campus how much people are using these types of technologies. So obviously you can't at the moment open your newspaper and not find any, somebody talking about what people are doing with CRISPR at the moment. I'm not going to go into, I could do a 2-hour lecture on CRISPR. I am not going to do that. So I'm just going to give you some basics just to make sure everybody's up to speed. So there really comes in 3 major flavors. So this is, as I say, changing by the day at the moment. One where you're predominantly using a highly active Cas9 nuclease that will induce a frameshift DNA mutation and that is therefore a permanent knockout. So this is more like that, you're making at a single, you're going to make a change that is going to completely knock out a particular gene. If you design targeting the guide molecule, which is a guide RNA, correctly. So this information you're going to need, ideally,